Hello and welcome to the next part of the lesson on representation of transfer functions of dynamical systems into the standard state space form. In the previous part of the lecture, we considered the first companion form and the second companion form. Now in this one, we are going to consider the Jordan form representation of the system. And the Jordan form representation results directly from the partial fraction expansion of the transfer function. So there are two possibilities. One possibility is when the poles of the given system transfer function are distinct, and the other possibility is when they are repeated, they have multiplicity. So we consider the case 1 first, in which the poles are distinct. With that assumption we proceed. So we are given with the transfer function, which is like this: nth degree numerator polynomial and nth degree denominator polynomial, the ratio ys by us. So what we do here in case of Jordan form representation is we break the given ratio of polynomials, given fraction, into partial fractions, and thereby we get a constant term b0 because the numerator and denominator both are of the same order. So we get a b0 plus n terms of the form r1 by s minus lambda 1, r2 by s minus lambda 2, etc. And lambda 1, lambda 2, lambda n, these are the poles of the system, and r1, r2, etc. these are the residues in the partial fraction expansion. Having done that, then we can assume that each term like this, r1 by s minus lambda 1, itself is a transfer function whose output is y1 and input is u. Other one output is y2 and the input is u, and so on. So they are parallel subsystems giving outputs as y1, y2, etc. up to yn, and all have the same input, something like this. This is the one, this is the other, and so on. This is the last one. This output is y1, this output is y2, and so on. This output is yn. All receive the same input us. So we consider one of them, yis by uis, which is residue ri divided by s minus lambda I. If we do a cross multiplication of this, and we consider one after the other like this, so we have xi by us ri minus divided by s minus lambda I. By cross multiplication and doing the inverse Laplace transform, it will give first derivative of xi equal to lambda I xi plus ri times u, this way. And the outputs, as I explained in the previous slides, they are the sum of these outputs y1, y2, etc. And each one is having one state like this xi. So the output is formed by combining all the respective states x1, x2, etc. up to xn, and plus the b0 times u, this one. So what will happen is that the system will get represented into nth order state space representation. However, these lambdas will appear along the diagonal like this: lambda 1, lambda 2, lambda 3, etc. up to n, and r1 u1, r2 u, r3 u, etc. rn u are the respective inputs going to the subsystems. And of course the output is summation of all the respective components of output, so x1 plus x2, x3, etc. to xn, and plus the b0 times u. So the system is represented by x dot equal to ax plus bu, y equal to cx plus du, and this is this A is a diagonal matrix, and on the diagonal we have the poles lambda 1, lambda 2, etc. This is obtained when the poles of the system are distinct. Now, when the poles of the transfer function or system have multiplicity, we consider that case. So we take the same transfer function, however we assume that the poles are located at lambda 1, lambda 2, etc. up to lambda k with respective multiplicity of gamma 1, gamma 2, etc. up to gamma k. So lambda 1 is having a multiplicity of gamma 1. Lambda 2 has a multiplicity of gamma 2 and so on. And of course, these will add up to n. Gamma 1 plus gamma 2 etc. will add up to n, the system order this way. So in this case, the partial fraction expansion of this GS will be, of course, a constant term B0 will come, but we will have k transfer functions G1, G2, etc. And these will be each of them like G1, G2, etc. So ith of them will be a term like this, which is respective residues Ri1, Ri2, etc. Each one is represented into as many terms as the multiplicity. So ith pole was having a multiplicity of gamma I. So we have Ri1 divided by s minus lambda 1 plus Ri2 divided by s minus lambda 1, lambda I square, and so on. Ri gamma I, this is the last coefficient, divided by s minus lambda I power gamma I. So this is one of those, and such will be the representation of all. So we still continue considering GIS, and this GIS, which is YS by US, YIS by US, this is GIS is YIS by US, and this is equal to, now YI is broken as YI1, YI2, YI3, etc., YI gamma I, and each one divided by US like this, multiplying through Ri1, Ri2, etc., Ri gamma I. So the output of the ith, that G is coming as a summation of output of this gamma I subsystems like this. And of course in that we see that first one is Ri1 divided by s minus lambda I, this one. Second one is containing lambda I square. So what we do, we express in terms of this and this term. So we can see 1 by s minus lambda I is yi1 by us that we put, and we retain the other term. So yi2 by us is 1 upon s minus lambda I yi1 by us, and so on. So what it gives is that yi1 dot will be lambda I yi1 plus u, yi2 dot will be lambda I yi2 plus yi1. This is the difference. In place of u we have yi1, and of course in place of lambda yi1 we have yi2. So in this manner the outputs of respective blocks, they get represented. We identify them states. So this is taken as yi is taken as state 1, this is x1, this is x2, this is x3, etc. So we have corresponding x1 dot, x2 dot, etc. and it is represented in this form. x1, this yi1 dot is lambda I yi1 plus u. yi2 dot was yi1 plus lambda I yi2. This one I am trying to bring there, and so on. So this is the matrix representation. This is, and it is of special. Its appearance is special because the poles lambda I appear on the diagonal, and the sub-diagonal has unity 1, 1, etc. So this is the Jordan form block. One of the blocks is of Jordan form like this: lambda I on the diagonal and 1 on the sub-diagonal. And of course, the input has a 1 in the first row, and all other have 0. So this is how we get one of those subsystems. And if we club all of them, put them all together, then the system matrix A of the given transfer function, the corresponding system matrix A in the state space description, will be all those Jordan blocks put together, J1, J2, etc. up to Jk, and all those corresponding input matrices B1, B2, etc. Bk. So K Jordan blocks and corresponding input matrices and corresponding output matrices C1, C2, etc. And of course direct coupling matrix B0 will be there. Each of them, that Jordan we saw it before, it is the Jordan form matrix. Each block is of this form, and number of elements, number of rows and columns is exactly equal to the multiplicity, corresponding multiplicity. So there will be gamma I by gamma I square matrix. This has gamma I number of rows like this, and these are the gamma I entries like this. So this is how the system gets represented in the Jordan form when the roots of the denominator or poles of the system have multiplicity, repetition. We consider one example, which is this. GS is S plus 1 by S plus 2 square, S plus 3. So there are two poles, one at minus 2 of repetition 2, multiplicity is 2, and one at minus 3. This system we want to represent in the Jordan form. So if we break this into partial fractions, we will get three terms like this: 2 by S plus 2, other one containing S plus 2 square in the denominator, of course it is minus 1, the residue, and the last one, the residue is minus 2 and S plus 3. So this is the GS, and now each one of them is represented as output y1 like terms, output y2 and output y3. So y is comprised of y1 plus y2 plus y3 like this. So y1 by u, the Laplace transform, is 1 by s plus 2. y2 by u will be 1 by s plus 2 into this itself. So because it was 1 by s plus 2 square, so one of that is we have kept as it is 1 by s plus 2, and other one we have substituted by this. And of course third one is separate, distinct, 1 by s plus 3. Now each one we have to represent in the by the differential equation. So first one we cross multiply and take inverse Laplace transform. So that gives dy1 by dt plus 2y1. This s gives dy1 by dt. This 2 gives 2y1 equal to u. And dy2 by dt plus 2y2 gives y1. And this one gives dy3 by dt plus 3y3 equal to u. And when they are put assembled in the form of matrices, we get this diagonal matrix. This is the Jordan block 1, this is the Jordan block 2. This is J1, this is J2. J1 is of the size 2 by 2 because the eigenvalue at -2 or the pole at -2 was having a multiplicity of 2. Corresponding input matrix, this is corresponding to the first Jordan block, this is corresponding to the second Jordan block which has only one element. And this is the C matrix, this is the C matrix corresponding to the first Jordan block, and this is the C matrix corresponding to the second Jordan block, and of course the direct coupling matrix between input and output is 0. So this is the way the system can be represented in the Jordan form. Now we summarize this topic, the representation of transfer function into the state space, and before that the representation of state space model by transfer function. So what we have learned is how to obtain the transfer function of the system given the state space model, that C Si minus A inverse B plus D. This was the transfer function. And given the transfer function, how to convert it to standard state space forms. And we represented it by canonical forms. One of them was first companion form, other was second companion form, and third was the Jordan form. With that, we conclude this topic. See you again in another lecture. Thank you very much.